Hello, everyone. My name is Leo, and today I'm going to talk about how exception handling, this widely adopted technique, can sometimes lead to catastrophic latent failure, which take developers days or even weeks to diagnose. And I'm also going to show you ExChain that helps developers to diagnose such failures in minutes. We all love exception handling because this allows us to implement a robust system in minutes. And in this slide, I'm showing you this code example that tries to open a file from disk. However, if the file does not exist on the disk, the language runtime will alert the application by raising this file not found exception. Luckily, the developers has predicted this, and they handle this exception smoothly by catching the exception and assign a null pointer to the application. So we're good now. The application will continue run even though it encounters this file not found exception. But some of you may notice that the developer did not actually handle the exception correctly. If the application continues to run, when it tries to write to this file, when it actually tries to write to this file pointer, the application will crash with this null pointer exception. So to diagnose this failure is actually extremely hard because the root cause of this failure is really this file not found exception. But the failure that the developer observed is this is this null pointer exception, which is also the failure that is raised by the application. So the developer really need to construct this dependency chain among those exceptions to diagnose this failure. Unfortunately, such dependency chain is extremely hard to find. There are three properties of such failure that prevents the developer to construct this dependency chain. The first is silent exception handling. As we just see, the developer decides to just assign a null pointer to this file pointer without logging the file not exception at all. Secondly, the exception not only affects the control flow of the application explicitly, it also affects the data flow of the application implicitly. That makes the reasoning how exception affects the state of the application even more challenging. Finally, the location where the final failure occurs might be spatially and temporally distant from the root cause. In this example, the developer may the application may write to the file in different functions or even in different requests. So because of this, such failures are extremely hard to diagnose. That's not only the fact for this failure is not only extremely hard to diagnose, it's also prevalent nowadays in large-scale systems. As a study conducted by researchers from University of Toronto has shown that 92% of the catastrophic failures are caused by this incorrect handling of non-fatal failures. So this is a hard problem, and this is also important to diagnose. Unfortunately, existing failure diagnosing tools aren't really helping developers to diagnose such failures. And if you look at log analysis, it really relies on the logs logged by the application. So if the developer did not log all the exceptions in the application, it really cannot help the developer. Failure monitoring or request tracing, they can't understand the implicit data flow caused by the exceptions, and they cannot reason the distant exception propagation. There are a couple works that try to understand how exceptions affected the control flow of the application in the programming languages and software engineering domain. Unfortunately, they are not focusing on the implicit state changes caused by exceptions. And I'm going to talk about ExChain and how ExChain help developers, how ExChain solved those three challenging problems. So ExChain is an online monitoring system which uses low overhead instrumentation to the application. It proactively monitors all exceptions thrown by the application. And when an exception-dependent failure occurs, it reports all exceptions related to the final failure. So since we are trying to build this online monitoring system, there are two goals we want to achieve. First is low overhead. If this monitor introduces excessive overhead to the application, it will make the tool not useful. Second is accuracy. If the tool reports excessive false negatives, the tool will be not useful. If the tool reports excessive false positives, it will just overwhelm the developer. So the key ideas behind ExChain to solve the previous challenges are, there are three key ideas behind ExChain to solve the previous challenges. The first is proactive exception monitoring. As I just mentioned before, ExChain decides to proactively monitor all exceptions thrown by the application. And secondly, to understand how exceptions implicitly affect the state of the program, it performs affected and responsible state analysis for all exceptions. And finally, to track the propagation of the exception, it uses hybrid taint analysis, which achieves both low overhead and high accuracy. So for the sake of the time, I'm going to focus on affected state analysis and also hybrid taint analysis in this talk. Let's start with affected state analysis. As I just mentioned before, the goal of affected analysis is to understand how exception affects the state of the application. And if we go back to our previous example, when the file not found exception happens, the application will assign a null pointer to the file pointer. Otherwise, the application will actually get a valid file object. This actually gives us a really good strawman solution. If we have a recorded traces of normal execution and also a recorded traces of exception execution, we can maybe just compare the memory snapshot to understand which state is affected. Unfortunately, today, this solution is not feasible. As you may notice that comparing the memory snapshots is very expensive, and even recording the execution is also expensive. And finally, for some cases, the normal execution may just not exist. Maybe the application did not receive any workload that can trigger the normal execution before the exception happens. So to achieve both low overhead and high accuracy, our insight is to use liveness analysis as an approximation of the affected state. Liveness analysis is a well-studied technique that used by many compilers and static analysis tools. Their goal, the original goal of liveness analysis is to allocate stack frames for local variables. And our insight is that we can use liveness analysis to understand how live variables changes for exception flow compared to the normal flow. This gives us a good approximation about affected states of each exception. And in this example, assigning now to the file pointer will only be live when the file not found exception is thrown. So we can always treat the file pointer as affected by the file not found exception when this exception is thrown. Moreover, since this analysis is static, we can always catch the analysis result of, we can always catch this analysis result. And when the same exception is thrown again, we can just use the result without recomputing it. So now we have identified the affected state of the exception. And we still need to track how those states propagate to construct the dependency chain. To give you a more concrete example, let's see how the program executes after the file not found exception happens. The application may store the file pointer to some map. It can also pass it as a function parameter to other functions. And finally, when it tries to write to the file pointer, the program crashes. But how do we know that this file pointer that causes null pointer exception is the same file pointer that is affected by the file not found exception? Luckily, this is actually also a well-studied problem in programming language and software engineering domain, where the researchers try to understand how information flows through the application. And there are two traditional solutions for this. The first is static taint analysis, which performs static data flow over the application as an approximation of the data flow. And this introduces zero no overhead, but it cannot scale well for the large applications. On the other hand, researchers have also implemented dynamic taint flow, which performs instrumentation to the application to track the information flow dynamically. This gives us very accurate result, but unfortunately, it also introduced tremendous overhead. Now, the real problem for us is that we are trying to use this in our monitoring system, and how can we achieve both efficiency and accuracy in our information flow analysis? To answer the question, can we combine the pros from both static taint flow analysis and dynamic taint flow analysis? It turns out possible, at least empirically. Our insight is that the most inaccuracy from the static taint flow analysis is from tracking heap objects. However, in most applications, heap objects don't copy that much. This allows us to separate the tracking task for different types of variables. For local primitives, we can just use static data flow analysis. For heap objects, we can add exception labels if they are affected without tracking them. So tracking local primitives introduces no overhead to the application, and tracking the heap objects introduce very low overhead. This helps us to achieve both accuracy and efficiency. Before I move to the evaluation, let's go over the key ideas of ExChain. ExChain actively monitors all exceptions thrown by the application. It identifies affected states and responsible states for each exception to construct the dependency chain, and it performs hybrid taint analysis to handle the exception propagation. To evaluate ExChain, we collect 11 reproducible exception. We reproduced 11 exception-dependent failures from real-world systems, such as Hadoop, MapReduce, and FineAct. 10 out of those 11 failures are reproduced in production environment. And we are trying to answer two questions. The first is, how does ExChain compare to those existing failure diagnosing tools? The second is, how does hybrid taint analysis compare to static and dynamic taint analysis? To answer the first question, we compare ExChain with Gzota, a statistical debugging tool, and Slicer4j, a backward tracing tool. In our evaluation, ExChain identified the failure for 8 out of 11, identified the root cause for 8 out of 11 failures. And Gzota only identified the root cause for 2 failures. And unfortunately, Slicer4j cannot identify the root cause for any failures. Moreover, ExChain has less requirement to diagnose those failures. Gzota, since it's a statistical debugging tool, it requires both normal execution and failure execution to diagnose those failures. And as I just mentioned before, sometimes normal execution just may not exist. And Slicer 4J performs heavy instrumentation to the application, thus it cannot be used in production system. It requires the reproducibility of those failures. And to understand how hybrid taint analysis compare to static and dynamic taint analysis, we implement two more baselines, X-static and X-dynamic. They both use the affected and responsible state analysis we have just mentioned before. Yeah, our evaluation, X-static only introduces 6% overhead to the application, but it only identified the root cause for 2 failures. X-dynamic can identify the root cause for all 11 failures. This actually shows the effectiveness of our affected and responsible state analysis. But it also introduced over 1,000% overhead. So in our evaluation, ExChain only introduces 8% overhead, which is only 2% higher than the static approach. So as a conclusion, we have talked about exception-dependent failure, which is severe, prevalent, hard to diagnose. And we also talked about ExChain, how ExChain uses the affected responsible state analysis and the hybrid taint analysis, which achieve both low overhead and high accuracy. And we have already open sourced our implementation, and feel free to check out our paper. And I'm happy to take questions. Thank you.